My name is again Edis Glogić. So I did this research during my PhD studies, which I did between University of Waterloo in Canada and University of Bordeaux in France, for which I'm currently a postdoc. I did this with Professor Stephen Young and Professor Guido Sonnemann, which are my previous supervisors. So I will briefly introduce these two tools that I'm looking at and I'm trying to compare and combine. So first one is material circularity indicator, and then perhaps more familiar life cycle assessment method. I'll introduce my research objectives, and then I'll talk a bit more about methodology, which is kind of the main deliverable of this research, to try to combine and compare these methods together. And I will demonstrate the use of this framework to case of alkaline batteries. So material circularity indicator is a circularity indicator that is applied to the product level. So it can be applied to the product level and company level, but this is one of the first indicators that have been developed for the products. So in 2015 by Ellen MacArthur Foundation and Granted Design. So due to its kind of early conception, but then also because of its kind of comprehensiveness, it's being perhaps most established of all the circular economy indicators, and as such has received quite a bit of traction even in academic literature. So the way material circularity indicator function is there are kind of three main components that are measured. First one is total mass of virgin material. So how much of the virgin material or otherwise secondary material we need to use to produce a product. On the other side, there is a total mass of unrecoverable waste. So all the kind of waste fractions that from the recycling or from the use of recycled material efficiency. All these waste fractions, they are considered. So in terms of, whether we have this kind of linear flow of materials or these materials are returned. So this waste fraction addresses this aspect. And finally, we have utility, which is how intensively do we use product or how product is built to be intensively used. So how durably the product has been built. So taking these three criteria into account, the MCI is calculated. On the other side, we have life cycle assessment, which perhaps you are more familiar with, which is a method for systematic accounting of emissions throughout the product life cycle. So from the raw material extraction to processing, manufacture, product use, and end of life, we have a kind of collection of all the inputs and outputs from the system, and translation of these inputs and outputs to environmental impact categories or indicators, and then we get a comprehensive picture of environmental profile of the product. So the advantages of combining circular economy indicators, and in this case material circularity indicator with life cycle assessment, are multiple. Primarily, it is to identify environmental trade-offs of circularity choices. So if you apply circularity strategies, we want to still make sure that it doesn't create trade-offs to the environment. In turn, also there is a value to life cycle assessment analysis, because we kind of look at the aspect of resources, and therefore we broaden this environmentally oriented assessment, perhaps more towards kind of sustainability assessment. And then it's convenient because you can calculate MCI every time you carry out LCA analysis. So we identify a research gap in terms of their joint use. We identified two research gaps. One is related to representation of the methods, how methods can be represented together given their differences. But then more importantly, how this joint representation is affected by the methodological differences between methods, between indicator construct and the construct of life cycle assessment. and specifically we look at how the evaluation of secondary material quality loss affects either of the results. So by secondary material quality loss, I mean that specifically MCI is unable to look at whether the material is downcycled or is functionally recycled. So it basically mostly looks at the efficiencies rather than quality of material. So that summarizes in one research objective, which is to investigate how methods compare for different circularity strategies on a product case of alkaline batteries, while specifically drawing on differences in the results of strategies sensitive to evaluation of material quality loss. So to compare these two methods and results of MCI and LCA, we developed kind of a four-stage process. The first one is to identify various strategies that can be applied at different stages of life cycle of the product. These strategies are then put together in a single improvement routes and then used to be able to develop net circularity value, which is then used to normalize MCI values, so to normalize absolute MCI values. These normalized values can be then used with kind of more conventionally normalization of LCA results. And these two results that can be then compared and you can identify the most valuable scenario or improvement route. So we apply this particular framework to a case study of alkaline batteries. We have chosen alkaline batteries as kind of very interesting product from circular economy perspective. Given predominantly metal structure, metal materials used in battery, but then also because it's so widespread and it has various challenges from circular economy perspective, let's say. But then also environmental impacts because they do possess some of the heavy metals, and sometimes this is not even acceptable for landfilling. So as a first step, we identify several circularity scenarios. First one is the default scenario, so the baseline, where we don't assume any recycled content in manufacturing of batteries. We assume a specific recycling route, which I will describe a little bit later, and this is a mistake, it's a 48% of efficiency. And then we assume that this product is average product, so it doesn't have higher power output than other batteries, so it has average power output, and that's average utility. And then we identify a couple of improvement strategies. So first one is use of recycled content. We assume that 10% of the virgin material has been substituted by secondary zinc and steel, coming particularly from galvanized steel recycling through open loop. The second strategy is recycling. So we assume that there is improved material recovery from 48% to 83%. And this considers particular recycling route 1, which I'll explain a little bit later. And then the third strategy or third strategy scenario is that we assume increased lifetime of ore capacity of batteries by 10%. And finally, we also introduce alternative recycling scenario in order to kind of understand better, this evaluation of material quality loss. What is its influence on the differences in the results? And this is where we have a similar increase in efficiency, but we have a different technology. So we have recycling tool technology. So this improvement strategies, these circularity strategies, they are combined in improvement routes. So we differentiate between improvement route 1, and then we differentiate between improvement route 2. And I will show you why this is important now. So we compare strategies within improvement routes in order to realize, what is the most preferable strategy among alternatives. But then also it is helpful to compare different improvement routes in this particular case to identify how differences in evaluation of material quality loss affects the results. So we compare here two different strategy scenarios for recycling. So to explain a little bit process of life cycle of batteries a little bit more, so we have kind of conventional raw material extraction, manufacture, packaging, retail, battery use, and after battery has been used, they either go to landfill or they are collected for recycling, in which case we assume this particular recycling route, recycling 1, which recycles battery to 48%, following grinding and separation process, and eventually separation of steel and recovery of steel, and recovery of zinc oxide, whereas the manganese slag is considered waste and landfill. In the second improvement route, we have improvement of some of these processes and process parameters. So in this case, we have first improve of 10% of utility. So battery is built with more power. We consider 10% input of secondary material of zinc and steel from galvanized steel recycling. And then we consider that actually the manganese slag is not sent to the landfill, but it is used in a building industry to produce clinker cement. And then we have improvement route 2, which has similar parameters. Which has similar parameters as route 1, except that we look at a different recycling route. The efficiency increase is the same, but in this case we also recover steel, but on the other side we use the electrolyte and we used electrodes and applied converted to agricultural fertilizer. So to show our results, these four, I'll explain first what these four charts mean. These first three charts, they are related to life cycle assessment results, so human health, resources, and ecosystems. And on the right side, we have material circularity indicator. So what these charts represent? So we have these three different scenarios. So we have recycle content scenario, we have recycling and utility, and they're all given as incremental increase or decrease from the default scenario. So in this case, we have for the recycled content, so if you add 10% of the recycled content, we have actually increase in impacts by 1.51%. We have decreased impacts for the resources by 0.11, and we have again added environmental burdens for ecosystems by 1.96. This all corresponds to improve of circularity by some 11%. For the recycling strategy scenarios, we have decrease of impacts in all cases, but this decrease of impacts is relatively small, so from 0.06 to 1.64%. Which corresponds to increase in circularity by 14%. And finally, we have a strategy scenario of utility, which reduces impacts by 16.7% and improves circularity by 31%. Now, in this case, we compared two different routes. Specifically, we looked at, what if we applied different recycling technologies that happen to have the same efficiencies. So, we jumped from 48% to 83% from the default scenario to the recycling improvement route. And as you can see, first for material circularity indicator, we have given that the efficiencies are similar, we have identical improvement of circularity, but on the other hand, the environmental impacts are much different. So here we have, as we've shown before, a small reduction, and here in this case we have a much more substantial reduction of environmental impact. So by 10%, 35 and 56%. So to conclude, circularity strategies, we show that they could lead to environmental trade-offs, particularly when considering use of secondary material in product manufacture. Obviously, this is related to this particular case of alkaline batteries, but it is interesting to kind of showcase that, you know, the trade-offs are possible and perhaps likely in some cases. We also show that evaluation of material quality loss is carried out, since it is carried out differently by two methods, might undermine robustness of dual analysis. So we're shown on this last slide that, you know, depending of recycling route, that you know, materials circularity indicator is not so responsive, which in case of environmental impacts, they can vary much more considerably. And finally, I would like to acknowledge a few limitations of this particular approach, and this is that it does introduce value choices. So we have, you know, it's up to analysts basically to kind of decide which combination of strategies and which scenarios they would consider. And given these scenarios, you know, you can obviously get different results for MCI. So in that regard, I think, you know, this particular approach is more useful to be used perhaps internally within companies rather than to kind of substitute absolute value for circularity, which MCI already provides. And the second perhaps limitation is that, you know, you can call it limitations or just observation that this particular approach is more useful for comparing MCI with LCA results rather than combining methods, given kind of this several steps that are really needed to consider in order to carry out the analysis. So with that, I would like to conclude my presentation. This particular work is currently under review at the Journal of Clinical Production. So if you want to you know, continue and see a little bit more, because obviously there is much more details in the paper than I was able to put in the presentation. But if you want to follow up, hopefully we get it published there. Lastly, I would like to acknowledge a couple of organizations that, you know, supported financially this research back then, and also with the data. And I would like to thank you for your attention. I hope I'm still.
So what?
Okay. Sorry about that.
Yeah, you're still with us. Thank you very much for your presentation. It's very interesting. I'd like to invite anyone who's participating in this session to go ahead and post your questions in the chat box, or if you're able to unmute yourself, feel free to go ahead and ask your questions directly. I'll give a second here to receive any questions, either verbally or in the chat box.
Yeah, this is Joe Cresco from the U.S. Department of Energy. Very nice presentation. I think this was a very well organized and presented bit of work. I'm interested in seeing more details, so hopefully this will get published and I'll reach out to you separately. I had a quick kind of clarifying question. If you just looking at the general, what was the 10% increase in recycling content for steel? If you could maybe just kind of clarify that, is that over the the baseline? If you think about steel today, it has and I know you indicated that in your sort of your process flow diagrams that, you know, electric arc furnaces are you know, part of the mix now, and I can't remember the amount of recycled content that's sort of average in the US now based on the fleet of electric arc furnaces, but it's a pretty good amount. Is the suggestion there of recycled content use, presuming that essentially the you know, the average recycled content would be increased by of steel, the steel supply would be increased by 10% over the current baseline?
Yeah, so So yeah, thank you for your question. I think it's an interesting question because I had to think hard about it. But I would say so. The 10% use of recycled content relates to both uses of zinc and steel in equal amounts. So it's actually only 5% of steel, of secondary steel in the batteries. I would say that current use of recycled content for the companies, I think for Energizer, that is out for retail, so that you can buy in the supermarket. I think it's 4%, and they say they kind of pledge to increase the percentage of recycled material, recycled content in the batteries up to, I think, 45 or 50%. So it is not completely clear to which material do they refer to, but I would I think it relates both to steel casing and electrolytes. So I mean 40% is quite a lot. But so I decided to assume 10% as kind of not overly ambitious target, but it's still something that industry might be able to do.
Yeah, it's really interesting. I suppose the way I was thinking about that, I was assuming that it might just be the case, the steel case and the shell of the battery, and that not knowing sort of what the makeup is, if there's any sort of unique type of steel that they need to buy, or if this is just sort of coil steel that they buy off of rolls, and it's part of if there are some perhaps requirements that require them to buy steel with certain properties that are by default then maybe higher percentage of primary steel versus secondary steel. If I think about steel used, I think in like the automotive sector, for the basic, sheet steel, a lot of that, I think the percentage of secondary steel in that is much higher. So I guess it does get down to the details of like what type of steel they're buying and for what particular use. So yeah, something I haven't thought about either for those applications. And I guess so yeah, good stuff. One other very quick question that I had was, you've done this for alkaline batteries. Have you thought about or attempted to look at other battery chemistries, emerging ones, lithium ion and others, to sort of get a sense of the current state and future potential for circularity there for next generation batteries?
Yeah, I think in terms of I haven't unfortunately, but I think there are two kind of challenges related to obviously they're all energy storage devices, but they face different challenges in terms of improving circularity. So in case of alkaline batteries, I think the challenge particularly was that you have so many different technologies that you can recycle them, but the challenge is more about collection and more about trying to produce them cheaply perhaps, and then once you have bigger batteries, once you have car batteries, or if you look at perhaps some more steady stream of maybe mobile phone batteries, because mobile phones are perhaps more readily returned to or disposed as electronics, then you but I think then you face a technological challenge. But I haven't looked into these batteries, but I think it's really, this topic is really much related to the batteries. So I would probably like to do that, but yeah, at the moment this is not something I'm focusing on.
Sure, yeah, I'll just finish by saying that's a big area of current work and analysis that we are undertaking across the Department of Energy. The Vehicle Technology Office invests a lot in advanced battery technology. My office, the Advanced Manufacturing Office, also works with our other offices that are involved in everything from specific products that use recycled content, for example, to all the way to looking at rare earth elements. And across the department, we have a pretty strong and focused initiative now on trying to understand things like the potential for re-X strategies, recycle reuse, remanufacture, and trying to understand the trade-offs that come into play there. And I think, you know, you had made a good comment at, you know, with your conclusions about the difference, sort of, you know, whether you're trying to compare, like if you're, let's say, within a company trying to compare options, that frame of reference versus a much broader governmental perspective of thinking about the, you know, bigger supply chains, and where, you know, it makes sense to make interventions in terms of driving circularity to the beneficial ends, so that we don't, you know, end up choosing sort of circular economy approaches that have, you know, unintended and poor consequences.
Yeah, indeed.
So,
yeah.
Yeah. But good work. Thank you very much. I appreciate
agree
your
fully. Yeah.
presentation.
Thanks a lot for the questions. Appreciate it.
Yeah.